Hello everyone, it's Mr. Geringer again, and this unit is about networks, and this chapter is about trees. It's 7.1. Alright, before we can start our discussion about trees, we have to talk about what they represent. So we have talked about in the past Euler circuits and Euler paths, and Hamilton circuits, Hamilton paths. All of those were part of graph theory. Trees are also part of graph theory. They represent specific types of graphs. And we're going to start off by talking about how they're applied. So we're talking about networks now. A network is a connected graph or a tree. In normal IT or information technology terms, a network is a connection of computers. And you know, there's a lot more than just your computers connected to the internet. Today we have wireless, and they're connected to a wireless hub, but there's always pieces behind the scenes that connect these networks to the internet. We have switches, routers, hubs. Each one of those are connected either wirelessly or with wire, and that's how we connect to the internet. So a network, if you're thinking about in your mind what a network may look like, just imagine all of those computers connected to a box somewhere that connects directly to the internet. The PCs are the nodes. So these are the vertices. We're going to have a vertice that represent the PCs or the appliances like a printer or a hub. It used to be back, 25 years ago, when they had green screens or amber screens. Those were actually called terminals. So this is a lot of computer terminology here. But the idea here is that the end result of your graph, when you're branching out, the end result are the nodes. That's where everything leads to. You have many different individual nodes, and they are connected by wireless or wired Ethernet. And that Ethernet, or at least the wireless or the Ethernet, are called the links. These are how they're linked up. If you didn't have a link, there would be no point to the node. And by the way, I have the definition of the vertices as nodes or terminals. I'll probably call them nodes from here on out. So anyway, that's a quick overview of a network. The theme of this chapter, of course, is, as always, finding an optimal network. And when defining optimal, you want to think distance, because the cable is expensive and wireless has its boundaries. You might want to think time, if you're looking to speed things up. So there are a lot of possibilities. It's all optimal is defined based on your goals. So now we've got some more vocabulary. A tree is a network with no circuits. So think back your Euler circuits, think back your Hamilton circuits. Remember what they look like. A tree does not have any circuits. Okay? A spanning tree, if you think about the full graph, a spanning tree is simply a subgraph of that full graph that connects all the vertices of the network and has no circuits. And actually, let me go ahead and draw that. So this is a simple example of a tree. Same type of terminology. Remember, the dots are vertices and the lines are edges, but we're going to call them nodes and links. So that is a simple tree. It's a network with no circuits. If I had let's do a connected graph like we did last unit with 5 nodes. All right. A spanning tree may look like the blue here. All right, a spanning tree is simply taking the graph that is not a tree and turning it into a tree. Now, we didn't have to stop there. We could have let me draw my graph again. We had to stop there, but we could have drawn a different graph. Like maybe my spanning tree may look like this. Looks like kind of like a K maybe. But the whole point is that the spanning tree is a tree inside a full graph. Now, as we're looking at this, notice I had the same graph here, the completed graph with 5 vertices. The spanning trees, there are many on any particular graph. We're going to be working with a weighted network again. We saw that last unit about where we assign the links a cost, some type of cost. And a minimum spanning tree is that spanning tree that has the minimal cost. So I'm really excited about this unit because I used to work in this environment. But I should tell you, the trees are one of the most useful structures in discrete math. It is part of a graph, so we know it's part of graph theory. It's incredibly valuable to computer scientists. And as a computer programmer, I used to rely heavily on trees. Now, they were coded trees, but they were trees nonetheless. The idea of nodes and links were all in my job as a computer programmer. And I'll show you some examples here in a second. So here's a tree. Again, look at, it's called a family tree. You've seen it before. But look at its attributes. Our rule for a tree is it has to be connected. It is a graph that is connected. And it has no circuits. The nodes here are, of course, the family names, and the links are, I guess, the relationships. Here's another example of a tree that I didn't code for this, but if you could extend, this is talking about quadrilaterals, but you could do the same thing with alphabetizing names of books, or if you have a list of customers, you can use the same idea to sort your list of customers. This is a decision tree. If you look at the first point right here, I'm going to draw a figure. Let's draw right and then do like that. There we go. So that's my figure. I start up here with this node. Are there any parallel sides? Yes, there's a parallel side. How many pairs? That's 1, 2. We know there's 2 pairs. Well, 1 pair. Sorry, that should be 1. These 2 are parallel. There's only 1 pair. Are the 2 sides equal? No. Then we've reached the point of labeling our quadrilateral a trapezoid. So that's a decision tree. Each node has us make a decision, and based on the decision, we go down the link. And you guys should be well aware of this type of structure. If you look at it, it's ethane. All right, it is a chemical bond between hydrogen and carbon, and you use it in chemistry quite a bit. But it also relates to discrete math because we're looking at a tree. It's a network. It's a network without any circuits. You have nodes. You have links, which are the bonds. And so that's another example of a tree. Here's a possible outcome tree. Notice that we start at the root. At this point, let's say that it's something giving birth, so either it can have a boy or a girl. If it has a boy, then the next one can either be a boy or a girl. Let's say that it has a girl. This next one, maybe they have another girl. So basically, this is an example of a tree of possible outcomes when there are only two possible outcomes. So each node represents a deciding point of a possible outcome. And this tree has a few special names to it. It's a rooted tree because all of the lower nodes reach to the bottom. Notice we don't have anything going below this part right here. That's what makes it a rooted tree. It's also a binary tree because each one has two possibilities. And then we have this, another type of tree. It's called an expression tree. Now, I don't know if you guys have ever run into this. I hope not, because this would give me nightmares. We have an equation, this equation right here, and we can separate the equation. For example, if we separated it based on this, here is the minus, so it's the same thing as saying this minus this. And now that we've got this, we can separate here, and so there's that operator. That's an arrow, by the way. So we separate the 4 plus 6 and the 8 by the multiplication symbol, and then we separate the 4 from the 2 by the division symbol, and then we move over to here where we go even further because we can still separate 4 plus 6 using the plus operator. So this tree, this tree right here actually represents our equation. Don't worry, you won't have to see this again. Here's a bunch of examples of possible trees and not possible trees. So A, what do you think A is? Is A a tree? Think back on our rules. It is a complete graph with no circuits. This as one graph is definitely not a complete graph. Therefore, it is not a tree. B not only is not a complete graph, but it also has a circuit, so it is also not a tree. C looks like a tree, doesn't it? It certainly does. It looks like a tree, but then again, there are circuits, so therefore it is not a tree. And D looks like a huge tree, but it has 1, 2, 3 circuits, so definitely not a tree. E looks like a pretty good tree. There are no circuits. It's a connected graph. F looks like a big star. That's a circuit, or it has no circuits, so that's a tree. We talked about family trees in G, and we talked about chemical bonds in H. So these are good examples of trees. So we do have some properties of trees. Notice our trees are special types of graphs, so our Euler and our Hamilton stuff doesn't quite apply to these. But we do have properties. There is only one path joining any two nodes. Okay, notice if I go from Craig to Matt, there's only one way to get there. There's only one way to get from Marty to Kim. There's just one way to get from one vertex to any other vertex. Second property, every edge is a bridge. So every link is that special link that we've talked about in previous units called a bridge. If you remember, bridges, if you erase them, they create a disconnected graph. If I erase that particular link, Kim will be by himself an isolated node, and so therefore this is a bridge. But the unique property of trees is the fact that there are no circuits, and because there are no circuits, you know that every single edge or every single link is a bridge. So that's property 2. Property 3 says that if you were to count the vertices, or the nodes, and the nodes have n minus 1 edges or links, then you know that you have a tree. So that's n vertices, or 1, 2, 3, 4, 5, 6 nodes. So n equals 6. So the number of links is 6 minus 1, or 5, 1, 2, 3, 4, 5. So I definitely have a tree. But notice that there are some graphs that have these properties but are not considered trees. Looking at this one, you can probably tell immediately this is not a tree. If you didn't notice the circuit, then you definitely noticed that it was disconnected. But it has two reasons why it is not a tree. But if you were to count it, how many nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 nodes, so therefore there must be 9 links. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this particular tree, it conforms to one of the properties, and I'll leave it up to you to remember which one. Dun, 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 dun. It satisfied the properties, but it definitely was not a tree. That's why it's very important that you follow the rules first. In order to be a tree, it must be a network, a connected graph that has no circuits. If you check that part first, then you can start looking at the properties. And that ends this particular chapter.